When a charge is stored on a capacitor is of 1 coulomb, which is having a potential difference of 1 volt, then we can say the capacitance is 1 farad. What is the electric field? So, electric field can be defined as it is V divided by D, that is potential divided by the distance. 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by C4 and so on up to any number of capacitors when you connect in series will be equal to equivalent capacitance, that is 1 divided by Cs. Hello everyone. Welcome to session 6 of chapter 2 Electrostatic Potential and Capacitance. This is Swati from Department of Physics, Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. So in this session, let us learn about capacitor and capacitance. What is a capacitor? What it is used for? A capacitor is a device which is basically used to store the electric charges. So, storing of electric charges plays a very important role in AC and DC circuits. So, a capacitor is a device basically used to store the electric charges and it consists of two parallel plates which are separated by a small gap. So, this is the circuit symbol for capacitor. Suppose if the value of capacitor is varying or it is a variable capacitor, then it is given by an arrow mark. Now, what is capacitance? How it is different from capacitor? Capacitor is basically a device. But what is capacitance? Capacitance of a capacitor is given by the ratio of Q divided by V. What is C here? It is capacitance and Q is the charges stored on a capacitor. V is its potential difference. The SI unit of capacitance is farad, which is symbolically given by capital F. The other units which are used to measure this capacitance is 1 millifarad, that is 1 into 10 power minus 3 farad, 1 microfarad, that is 10 power minus 6 farad, 1 nanofarad, that is 10 power minus 9 farad, and 1 picofarad, that is 10 power minus 12 farad. Now, we can define what is 1 farad. When can we say the capacitance is 1 farad? When a charge is stored on a capacitor is of 1 coulomb, which is having a potential difference of 1 volt, then we can say the capacitance is 1 farad. So, the capacitance is said to be 1 farad when the charges accumulated on the plates of a capacitor are of 1 coulomb and the potential difference is 1 volt, then it is 1 farad. And what is the role of this capacitor in any circuits? So, this is basically about capacitor and capacitance. Let us now learn about the parallel plate capacitors and the combination of capacitors, how to produce the effective capacitance by combining number of capacitors in different ways. So, now we are studying about the capacitance of a parallel plate capacitor. So, what is the meaning of parallel plate capacitors? So, it consists of two parallel plates separated by certain distance. So, the name parallel plate capacitor. Now, we have to find what is the capacitance of a parallel plate capacitor. So, let us now take a parallel plate capacitor C. So, two plates are used to store the electric charges. I will take it as plus and minus charges and they are separated by a distance D. So, let us say E is the electric field between these two plates. So, I hope the diagram is clear. So, here plus Q and minus Q are the charges and D is a small distance of separation, that is we can say distance between plates. Let us consider A as area of each plate and E is the uniform electric field. We have to find the capacitance of a parallel plate capacitor, that is C, which is equal to Q by V as we all know. But what is the electric field? So, electric field can be defined as it is V divided by D, that is potential divided by the distance. So, now we have considered two parallel plates, but we know the electric field due to an infinite plane sheet is given by E is equal to sigma divided by 2 into epsilon naught. Now let us consider these two plates as two infinite plane sheets on which the electric field is producing. So here we have two sheets, and hence I can write it as E is equal to sigma divided by 2 into epsilon naught plus 2 sigma divided by 2 into epsilon naught. And this is nothing but 2 sigma divided by 2 into epsilon naught. This and this will get cancelled, and I remain with sigma divided by epsilon naught. So this is the expression for E. So now I have E is equal to V by D, that is an expression for electric field, and E is equal to sigma divided by epsilon naught. I'll take it as equation 2. Now from equation 1 and 2, we can write V divided by D is equal to sigma divided by epsilon naught, or we can write it as V is equal to sigma D divided by epsilon naught. So this is my equation 3. This V is useful in finding the capacitance. That is, we know that capacitance C is equal to Q divided by V. So I have Q divided by, in the place of V I am substituting this sigma D divided by epsilon naught. But according to surface charge density, sigma is equal to Q divided by A, or Q is equal to sigma into A. Now substituting this Q is equal to sigma A in this expression, we get C is equal to sigma A divided by sigma D divided by epsilon naught. Sigma and sigma will get cancelled, and this epsilon naught move to the numerator. So we get C is equal to A into epsilon naught divided by D, and this is an expression for capacitance of a parallel plate capacitor, which is given by C is equal to A into epsilon naught divided by D, from which we can say what are the factors on which the capacitance of a parallel plate capacitor depends. It depends on area of each plate. It also depends on the medium, the dielectric medium between these two plates. It also depends on distance. So to increase the capacitance of a parallel plate capacitor, we must increase the area of plates, and the distance between these two capacitors must be very small. So this is how we can conclude the capacitance of a parallel plate capacitor. So now let us move on to the next topic, that is combination of capacitors. We came to know what is a capacitor, a device which is used to store the electric charges. See, we can make use of these capacitors by connecting them or by combining them in various ways to increase the effective capacitance or to vary the effective capacitance. Two simple ways to combine the capacitors are series combination and parallel combination. So let us now study the capacitors in series. So what happens if we consider or if we connect two capacitors in series? This is my capacitor 1. I'll take it as C1 and C2. So two capacitors are said to be in series combination when they are connected end to end such that the charges on each capacitors are same, which means Q1 and Q2 for both the capacitors are same, but the potential is different. So the potential difference between this capacitor is V1 and the potential due to capacitor C2 is V2, and these are connected to a external source. You can observe here the capacitors are connected end to end such that the net potential in the circuit, that is V, is equal to sum of potentials due to two capacitors, that is V1 plus V2, but the charges on the capacitors remains same. So now according to the condition, total potential is equal to sum of the potentials due to the capacitors C1 and C2 respectively. So in this circuit, C1, C2 are the two capacitors, V1 and V2 are the potentials due to capacitors C1 and C2 respectively, and Q is the charges. So here we will be having plus and minus charges in two capacitor plates. Now from the expression C is equal to Q by V, we know what is V? V is equal to Q divided by C. So now let us substitute this for V1 and V2. For V1 it is Q divided by C1, because why it is not Q1? Because the condition says the charges remain same for both capacitors C1 and C2. Since the capacitors are different, I have taken C1 and C2, it is Q by C1 for V1. For V2, it is Q divided by C2. Now, if these two capacitors are replaced by a single capacitor of capacitance C, since it is a series combination, I have taken it as CS. then we can write the same expression for effective capacitance. The equivalent capacitor is connected instead of two capacitors. So we can also write the expression for this, that is V is equal to Q divided by Cs. So this is my equation 1 and this is my equation 2. Now from equation 1 and 2, since in both these equations we have V term in the LHS, so we can equate these two equations. So from first equation I have Q common and I can write it as 1 divided by C1 plus 1 divided by C2, which is equal to second equation, it is V only. Both the equations we are equating for V, so it is Q divided by Cs, or we can write it as Q into 1 divided by Cs. So in these two expressions, so in this equation Q and Q at both the ends are same, so we can cancel and we remain with 1 divided by C1 plus 1 divided by C2 is equal to 1 divided by Cs. So this is the final expression for a capacitance when they are connected in series. So 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by C4 and so on up to any number of capacitors when you connect in series will be equivalent to equivalent capacitance, that is 1 divided by Cs. So this is the final expression when the capacitors are connected in series. You can connect any number of capacitors in series and you can arrive at this expression. So now let us study about the combination of capacitors when they are connected in parallel. So parallel combination of capacitors, circuit diagram is like this. So parallel combination means when two capacitors are said to be connected in parallel when they are connected at two common points. When they are connected to two common points, this is my capacitor C1 and this is C2. So these two capacitors are connected in parallel in such a way that the potential between these two capacitors remains same, which means V and V for both the capacitors, but the charges due to each capacitors are different, which means the net charge, total charge is equal to sum of the charges on both the capacitors, that is Q1 plus Q2. Now from the expression C is equal to Q divided by V, we can write Q is equal to C into V. Now for the first capacitor, it is C1 into V plus for second capacitor it is C2 into V. It is not V1 and V2 because V is same for both the capacitors. So we have Q is equal to C1 into V plus C2 into V. In this V is common, so we can write C1 plus C2 and this is my equation 1. When these two capacitors are in parallel, when it is replaced by a single capacitor of capacitance Cp, then the equation can be written as Q is equal to Cp into V and this is my equation 2. Now equating equation 1 and 2, we can write both are Q and Q only. So we can write V of C1 plus C2 is equal to Cp into V. We can cancel V and V and we remain with C1 plus C2 is equal to Cp. And this is the expression for effective capacitance when the capacitors are connected in parallel. So if you want to increase the capacitance in any circuit, you have to go with this combination, which means the capacitors should be connected in parallel to increase the capacitance because it is the sum of all the capacitance due to individual capacitors. So from this we can conclude to increase the capacitance in any circuit, which combination should we connect the capacitors in, and to decrease which combination should we opt. So these are the very important topic from the chapter Electrostatic Potential and Capacitance. In the next class, we will study some more interesting concepts. Until then, keep learning all of you. See you all in the next session. Thank you.